These are Unit 7 notes for chemical reactions in chemistry, and this is part 2, which will be over types of reactions. Actually, it's part 3 because we already did basics on reactions and we did balancing, and this is types. Sorry, but this is the second recording. Maybe I should put it that way. This is the second recording over chemical reactions. And this is going to be talking about the specific types of chemical reactions. And there are 5 types of chemical reactions. We have our combination, and then we have our decomposition, and then we have single replacement, and then we have double replacement, and then we have combustion. Now, combination reactions can also be combination reactions can also be called synthesis reactions, and so yes, so we'll talk about that. All right. So a synthesis reaction, which is also known as a combination reaction, is really just the combination of 2 or more substances to form a compound. So you'll always have 2 or more reactants, but you'll only have 1 product. So the basic, general form of it will be A plus B yields AB. So again, there's multiple reactants, but just a single product. All right. So the product in the reaction will have different properties than either of the reactants that formed it. Primary example would be when we take sodium and we take chlorine. Sodium is a white solid substance that has to actually be stored underneath oil because it's very reactive to water and even just the water vapor in the air. And then chlorine is a green gas. So when they're separate from each other, both of them are very toxic to us. All right. Now, when it gets combined, it creates NaCl, which is table salt, which all of us need and all of us consume. So it's kind of interesting that when they get put together, their properties are very different. So on the reactant side, we have Na by itself. The Cl has a subscript of a 2 because it's diatomic. It's one of our H Broncliffs. And then NaCl was named using the formula was written using our information from Unit 5, where we talked about Na has a positive 1 and Cl has a negative 1, and you crisscross. Once we get all the subscripts written, then we will talk about, is it balanced? Well, we have 1 Na over here, we have 1 Na over here, so that's good. We have 2 Cls over here, so that would mean that we need to put a 2 over here to get 2 Cls over here. But once we do that, we have 2 Nas on the product side, so we now need to put a 2 there. So balancing is something that we always have to do, but it's one of those things that we create the product, we look up the charges, we do the crisscrosses, we check for diatomics always, and then we balance accordingly. Okay, here's another one, iron and oxygen. Okay, iron, I will tell you, is actually a transition element. So unless I told you its charge, you wouldn't know it from the periodic table. But I'm going to tell you it's a positive 3. Okay, so when I say it's a positive 3, oxygen's a negative 2. So when I crisscross, I get the subscripts of this on this side. Oxygen's a diatomic, that's why it's by itself over here. Or when it's by itself, that's why it has the subscript of a 2. Then we have to balance. Well, we have 2 irons on the other side, so we're going to put a 2 right there. Then we have 3 oxygens on one side and 2 on the other, so we have to look for a common multiple, which would be 6. So we'll put a 3 there, and we'll put a 2 there. But when I do that, 2 times 2 of my irons now makes 4, so that makes my original 2 of a coefficient in front of iron wrong. So I'd have to change that to a 4. And that's why I always recommend you use a pencil when you're balancing. All right, then we have Al and Cl. Again, aluminum is a shiny solid metal, and chlorine's a green gas. But then it creates something called aluminum chloride, which would be Al's a positive 3 and Cl's a minus 1. So when we crisscross, we end up with AlCl3. We don't ever just bring the subscripts from one side to the other. No, 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 no. Don't do that. So then we look to see if it's balanced. So Al1, 1, Cl2, 3. So we have to look for a common multiple, which would mean we put 3 here, 2 there. That messes up my Als. So then I have to put in a 2 there. Okay? This one I'm not going to do. It creates it would be a compound, but it creates an acid, and so we aren't going to do ones like that. So I'm going to skip over this example in our notes. All right, the next type of reaction is a decomposition reaction. Now, decomposition reactions are breaking down the substance into two or more other substances. So the cool thing about this one is you only have one reactant, and it breaks down into two or more products. So its general format AB breaks down into A and B. Okay. So I'm going to skip that first one because, again, it's kind of an odd one, and you won't be held responsible for acids in this unit. So this first example that I'm going to do is KCl. So I will break it up into the individual elements that it is, and that would be K and Cl. Now, Cl is one of our H Broncliffs. So because it's one of the H Broncliffs, it's a diatomic, which means when it's by itself, it has to have a subscript of a 2. So once I make sure that I've broken it into its pieces and I've checked for diatomics, now I balance. So I'm going to need a 2 right here to balance out my chlorines, which means I'm going to need a 2 right here to balance out my potassiums. Then I have HCl. So I'm going to break those. That's hydrochloric acid, but we can talk about how it will break down because it breaks down into its single elements of just hydrogen and chlorine. Both hydrogen and chlorine are diatomics, though. So chlorine needs a subscript of a 2, and hydrogen needs a subscript of a 2. And you are going to be expected to do this. Like, I'll just give you the reactant information, and you're going to have to break it down into the products. Okay? Then I have to balance, which would mean I'd put a 2 right here, and now it's balanced. Okay, single replacement reactions. We have one element replaces another element in a compound. So this would kind of be like the couple that's dancing and the guy comes and cuts in and dances off with the girl and the other guy's by himself. Okay, so we have an element and a compound, and then we're going to have an element and a compound. Now they can be in any order. It could be the compound and the element and then the compound and the element, but it's going to be that you have an element or a single element and some sort of compound as reactants, and you have a single element and some sort of compound as product. Okay. So here I have zinc and hydrochloric acid. Okay. And so zinc is a transition metal. Hydrogen is a positive ion. So zinc is going to look at cutting in on hydrogen because we always want to create compounds that are positives and negatives. So when we look at it, here, let me think about it like this. So zinc is going to want to come in and bump hydrogen out. Okay, on the back of your periodic table, which all of y'all should have a printed copy of. If not, it's on my Google Classroom, or it's on my classroom, or it's available to you through various sources, and you should be able to find which one we use so you can print it and have an accessible copy. But on the back of the periodic table is an activity series. And it's what we use to see if zinc can really bump hydrogen out. So you look on the activity series, and what it is you find zinc and put your finger on it, and then find hydrogen and put your finger on it. And if the single element is higher on the activity series than the one it's trying to replace, then it will happen. So zinc will bump hydrogen out. So when it bumps hydrogen out, it will make it to where it is zinc chloride and hydrogen gas. Well, zinc, the way we got this was zinc is a positive 2 charge. We know that from our periodic table because zinc is always a positive 2 charge. Chlorine is negative 1. So then we crisscross those down, and that's how we create that compound there. And then hydrogen is a diatomic, so it has to have the H2 when it's by itself. We don't ever worry about what the subscripts are on the reactant side for the subscripts on the product side. Okay? The subscripts on the product side are created according to diatomics and formula writing rules. So after we get the products, we'll need to balance, which means we would need a 2 right there. So that's the key thing about these. You're going to look up if the single element is higher on the activity series than the one in the compound. If it is, the reaction will happen and you create the products. Once you create the products using using your diatomics and formula writing rules, then you balance. So now we're going to look this up. Now this one isn't on your periodic table, but I do want you to know that for the halogens, which is group 7A on the periodic table, we have fluorine, chlorine, bromine, and iodine. Okay, and they have increasing activity, meaning, again, anybody higher on the list can replace the others. I always say that these are the fluorine, the halogen sisters, and that fluorine is super cute, and she can steal any of her sister's boyfriends if she wants to. Chlorine can only steal bromine and iodine's boyfriends, okay, but bromine can steal iodines. Poor little iodine, she's the youngest and she can't steal anybody's boyfriends. But, so that's kind of how I always kind of look at it, and that's a fun little analogy that I use with it. But, so now looking at this list, and I might even add this to my periodic table above the activity series. So I look and I say, okay, chlorine is here and iodine is here. So chlorine is higher, so chlorine's going to be able to replace iodine. Remember, it's going to be like elements. So this one, remember, was a positive replacing the, I didn't draw a very good arrow there, the positive. This one is a negative replacing the negative. So that's kind of the key thing to remember. So this is going to work. And so when it works and chlorine bumps iodine out, then it becomes potassium chloride and iodine. Iodine is a diatomic, so I have to have a 2 with it when it's by itself. Potassium's a positive 1, chlorine's a negative 1, so then when I do my crisscross, then I create KCl. Then I have to look at balancing, which will mean I have to put a 2 there to balance out my chlorines, and I'll have to put a 2 there to balance out my potassiums and iodines. All right. So again, to determine if a single replacement reaction will even take place, you have to compare the activities of the elements involved. For metals, we'll use the activity series, which again is on the back of your periodic table. And a metal will replace any metal below it. So if it's higher, it will replace it. I also am including, like I said, the halogens. And the halogens are fluorine, chlorine, bromine, and iodine. And again, anybody higher will replace. So will sodium replace chromium? Well, sodium's here, chromium's here, sodium is higher, so yes, it will replace. Okay? So again, iodine and sodium chloride. Is iodine higher than chlorine in the halogens? Your answer should be no, iodine's not, because iodine's on the very bottom. So that would mean that no reaction's going to happen here. This is not going to be possible. Then I have magnesium wanting to replace gold. So I look up magnesium on my activity series and I look up gold, and yes, magnesium is higher, so then I'm going to have to create compounds. So I bump gold out, magnesium has a positive 2, nitrate has a negative 1, so when I crisscross, this becomes the subscripts because this is the new formula for magnesium nitrate. Then I have to balance, so I'm going to have to put a 2 there to balance out the nitrates, and then I'll have to put a 2 there to balance out the golds. Then K, Br, and F2. So is F higher in the halogens than Br? Yes, it is. So it will bump Br out. When I write my formula, K is a positive 1 from my formula chart because it's in cation because it loses electrons. And fluorine is a negative 1 because it gains electrons and becomes an anion. All right. Bromine is an H Broncliffe, so it has to be Br2. Once I get the products written properly and I check for diatomics and I follow my formula writing rules for ionic compounds, then I look to balance. So I'm going to have to put a 2 over here in front of the KF to balance out my Fs. And then I'll have to put a 2 in front of this to balance out my Ks and my Brs. All right, so my next one, I want to see if copper will replace magnesium. So I look up copper, I look up magnesium. Copper is not higher on the activity series, and so this will be a no reaction. All right, then we have double replacement reactions. Two elements replace each other in compounds. So it's a lot like dancing partners that switch. Okay, so we have A and B plus C and D, and then we get A and D and C and B. So it literally is the positives switch, negative partners. Okay, so sodium sulfate and barium nitrate. So sodium and barium are going to switch partners. Okay, so when they do that, I have the positive of sodium and the negative of this one, and when I look up their charges and do my formula writing rules, and I crisscross, I'll end up with sodium nitrate as NaNO3. And then I'll have barium, which is a positive 2, and sulfate, because it's the positive of this one and the negative of this one. So I get a positive 2 and a negative 2, which if they're the same charge, they cancel out, so it would just be BaSO4. And so my products would be as follows. After I do that, then I have to balance. Really, I have 2 NaNO3s here, so I have to have 2 over here, which means that I have to put that 2 there. That makes me have 2 sodiums. Well, I have 2 sodiums on this side, so I'm good to go. All right, so again, the positive of this compound is Na, the negative of this compound is NO3, so we'll combine those again. They're both positive negative 1, so it just becomes NaNO3. Then for this one, the Fe is the positive and OH is the negative. Now, Fe is a transition element, so some of y'all will be like, how are we supposed to know what its charge is? Well, if you remember, undo the crisscross. So this 3 right over here on the nitrate came from the iron. So we would say Fe positive 3 and OH negative 1, which would then, if we crisscross, is FeOH3. Okay? So then we have these as our products, and we go ahead and look for balancing. There's 3 NO3s over here, so we have to put a 3 there, and then that causes us to have 3 sodiums and 3 OHs. Well, this is 3 sodiums, and this is 3 OHs, so we're good to go. All right. Now, I will tell you, in order for a double replacement reaction to actually take place, one of the products must be an insoluble solid, a gas, or a molecular compound. Now, there are solubility rules on the back of your periodic table, which list common insoluble substances, but I am going to tell y'all, in our chemistry class right now, we are going to give you reactions that are going to always occur for double replacement reactions. So you won't have to predict what the insoluble solid is or any of those things. So just to let you know. Okay, so again, this is what the insoluble compounds kind of chart looks like, but I won't be holding you guys I won't be testing you guys on that. Maybe I should say that. So I'm going to skip past this because we're not actually doing that. So combustion reactions are our final type of reaction that we have, and it's an exothermic reaction in which a substance combines with oxygen, forming products in which all elements combine with oxygen. Now, it is burning, so energy is usually released in the form of heat or light. The general format is that you have some hydrocarbon plus oxygen, and you create CO2 and H2O. Okay? So those are always going to be your products, almost always, when we're talking about combustion reactions. But for us, those are going to be the products that we're going to have. So our examples, I have C3, and that's why it was CX earlier in the general format, and H8. So this is a hydrocarbon. It's going to be combined with oxygen, and it's going to produce CO2 and H2O. These are always the combustion reaction products that we're going to be dealing with. After that, we have to balance. So we balance our carbons first. You always need to balance in carbon, hydrogen, oxygen order. So that has us have 3 carbons, and this would make it to where we have 8 oxygen or 8 hydrogens. 4 times 2 would be 8, and then we count up our hydrogen or our oxygen, excuse me. So we have 3 times 2, which is 6, plus another 4, which would give us 10. So we could put a 5 there. Okay, this is also a hydrocarbon. Notice it also has an additional oxygen. Okay, this is actually known as glucose. All right, it's added to oxygen, and we get CO2 and H2O. So again, we have to balance. So we would put a 6 here to balance our carbons. We'd put a 6 here to balance our hydrogens, which then we'd need a 6 here to balance out our oxygens, because we have 12 oxygens here, but we have another 6 here. So 6 times 2 makes 12 here, plus this other 6 over here. Okay, we could also have something like magnesium and oxygen, but I will tell you we're not going to test you on ones like this, but it creates magnesium oxide, so it's a little bit different. It's kind of like a synthesis reaction, but anytime you combine something with oxygen, it's actually known as a combustion reaction. But again, we won't test you on this in our chemistry classes. Okay? And that would be it for your types of reactions. If you have any questions, let me know and we'll get together for tutorials.